So thank you very much for the introduction. My name is Maximilian Luczak. I'm with the consulting and projects team at Math2Market. And for this particular case, I work with a couple of partners in the publicly funded project DELFIN, which is aiming to develop a validated simulation model for all solid-state batteries. First of all solid-state batteries are a relevant topic in battery development at the moment. You get news about battery breakthrough, 600-mile charge in 9 minutes, a 20-year lifespan, which is quite something big that you can promise, and higher proof EV batteries. So solid-state batteries being able to run without the flammable electrolyte, which is all great news to get. And of course, this all-solid-state battery technology has a lot of promises. And here we will take a look at our approach in this project to tackle the both potential benefits, but also take a look at potential challenges that you will face when developing these kinds of batteries. So as a cornerstone for future or modern infrastructure, portable electronics, and energy systems, ASSB technology could be of a great benefit with the enhanced safety factor. You don't have any flammable electrolytes in it. You have a high energy density and also the promise of improved longevity. It is just overall a great potential that you want to harvest. But the challenges, of course, are also there. You have potential issues with the interfaces between the solid electrolyte and the active material. The manufacturing can be quite complex. Most of the materials used in the solid electrolytes are both not hydrophobic, but very sensitive to humidity as well as oxygen. And the materials that are used at the moment may also be limited, so you may want to look into different materials that you can use for this technology. And all in all, smart methods and research and development are very important to make this endeavor a successful one. Here I want to talk about the approach we go for in the DELFIN project. First of all, we had to make sure that we understand the solid electrolyte, which we haven't really used before in GeoDict. In this case, we settled on LPSCl, and in combination with NMC 811, we picked LPSCl since it is a commercially well available solid electrolyte, even though it has some features, especially in the imaging qualities, that make it a little bit inferior to, example, LPSCI, the iodine salt. We still wanted to use the LPSCl in this project because we think it will be more probable to be used in a real-world scenario. We wanted to develop a way to digitalize these these kind of structures in a more reliable way. So at the moment, as Roman talked about, having a 3D scan of these structures usually requires FIB-SEM technology. FIB-SEM is quite expensive. It's quite difficult to get your hand on. And so we wanted to also move forward a way to use more available methods like micro-CT scans. And of course, we wanted to take a look at what the batteries actually can do that we want to simulate, or what ultimately which we want to also produce in this project. So we needed a good and solid way for BatteryDict to handle the solid electrolyte. So this is an overview over what I would call a typical workflow that you will have in GeoDict. Step one is that you have to digitize your material. both to understand your material better, but also as a starting point for your material development. You need to know where you come from if you want to improve the material that you have. So we have a dedicated sub-project which is taking care of producing good scans of the cathode materials that are used in this project. Secondly, we want to analyze the scans that we have. We want to understand as much as possible about the materials that we're using. Fortunately, GeoDict already has a wide array of analytics that we can use to tackle this problem. And so we get the statistical data as well to create a digital twin. The third step would be validating our results with experimental data. Fortunately enough, we have an experimental group in this project, which is providing us with both input parameters, which we use to design our materials in GeoDict, and also they provide us with results which we can then lay against the results that we get out of GeoDict. And the last, also very important step is that we actually need to be able to design new kinds of cathode materials. For this is imperative if we want to make use out of GeoDict, because we want to improve the material that we got. So we are working on a cathode designer, which specifically is geared towards the use in all solid state batteries. This morning you already heard of this approach by Dr. Orkun Furat from Ulm University, who is part in this project. And if we take all of this together, that we can understand our materials, we analyze them, we can validate it, and then design new materials, and can, so to say, drive the loop again and analyze the new materials, see where we can improve, then we are actually doing innovation with the help of GeoDict into creating better materials for the future. So let's go through these steps one at a time. So first, about the digitization. Here we work together with a commercial partner. It's called RJL Micron Analytics, and they provide us with micro CT data of the materials which were produced by our partners at the Justus Liebig University in Gießen. And what we needed to do is two things. So first of all, the micro CT resolution is right on the edge of what you can use for this problem that we are facing here. And we needed a solid way to improve our image quality. Fortunately, RJL is able to provide us with two different reconstructions of the same scan. So we have the standard scan, which gives a good topographical resolution, which is here seen on the left. And we have a free field phase contrast reconstruction of the same scan, which is basically giving us a better contrast between background and other components which we find in the solid state battery. In this case, this is important because the as you can see, the contrast between the LPSCL is not always very high against the other materials. So we are very happy that we get these two different image stacks to use in this segmentation approach. So what we are doing is we basically take these pictures into our software. In this case, I started to train a UNet 3D model, AI model, to segment this. You can see you basically just mark your areas depending on what you believe they are. So you can see the pore is unfortunately light gray, which is really bad with the other contrast here. But in red, we have the active material, and in green, you will see the solid electrolyte. This is kind of hard to do when you only have one scan, but if you can switch back and forth between the free field contrast and the high resolution scan, you get a better idea what you're actually labeling. And in the end, we can take the segmentation of both channels, the standard and the free field contrast, and put this into a dual channel segmentation. It's basically the same approach that Roman showed before regarding the secondary electron images he used for the FIBSEM. So you can see, maybe I put your attention on this spot here. This is, when you see it with your eye, you can pretty easily indicate that this is probably void space. Unfortunately, the single channel segmentation didn't agree with my eye test on this one, but if we use the dual channel segmentation, have the free field phase contrast image in the segmentation as well, we get a way better result. So in the end, we can take the relatively cheap and easy micro CT scan with 2 different reconstructions, and through the use of the dual channel approach, we are able to enhance our image quality significantly. Of course, this is still work in progress. The pictures that you see right here are taken from a powdered sample. It's not a compressed cathode sample yet, but we will have this in the near future. And then we can work again on the improvement of this imaging technology towards a better understanding of the cathode. So here I have 2 images. So this is the powder one that I just showed you, which has still about 25% of void space or empty air inside of the structure, which is of course not what we want to have. So I also had, fortunately, I had a FIBSEM scan of a all-solid state battery from the same group in Giessen, and this one was a compressed structure, so we see 7.2%. This is much more what we would aim for, but I'm fairly confident that with the compressed structure and the micro CT scan, we will actually be going towards the same boundaries in this case. So for the further slides that I show, I have used the FIBSEM scan because this structure is just way more representative of a actual ASSB cathode. So let's go to the analyzation part. Fortunately, here we can use lots of features which are already inherently in GeoDict. So we can take a look at lots of geometric parameters. We have the porosity, pore size distribution, grain size distribution, surface area length of contact lines, tortuosity. These are all geometric parameters which we're very confident that they are calculated correctly given the structure that we got. We have lots of transport parameters. We can predict the conductivity, the diffusivity, lithium path of single particles. We can do all these analysis on the structure that we have available. And finally, we can also look at the way this structure behaves in a battery. So we can have the charge curves with different charge rates simulated on the structure, the 3D lithium concentration during operation. We have fast simulation using homogenized models and instant estimation of charge curves. So this is what we can all do with the structure once we got it. So we already gain a way better understanding of the structure and of the properties of the structure immediately from this. So again, I have to show a work in progress slide. So we have implemented all the necessary steps that you need to put into calculating all-solid state batteries with BatteryDict. Here's an example of experimental data, which we get provided by the Justus Liebig University. And here's an example of just 3 charge rates on the same structure, which we used in this case here. So the new features which you will have in GeoDict. So currently, the solver equations have been modified to work better in with solid electrolytes. So the fusion and migration terms are not required when you look at ASSBs. So as soon as the as BatteryDict detects that you're using a solid electrolyte, we will switch to the required calculations that have to be done. The transfer number T plus is always 1. So charge conservation and electron neutrality terms are also simplified. The exchange current density between the active material and the solid electrolyte is implemented in the material database. So when you, for example, pick NMC 811 and we have the available data with us, we implement this into our database. So you can add, you can pick LPSCl as your electrolyte with the maximum exchange current density, which we have evaluated for this substance. And of course, you can also add your own electrolytes into this calculation. So these materials, namely NMC 811 together with LPSCl, will be shipped with GeoDict 2025 and allow you to do the simulations in BatteryDict. So this is more of the technical terms that we did to improve this. So we, in general, exchanged the Butler-Former rate constants, which were present all over the BatteryDict GUI. We replaced this with the maximum exchange current density. So this is a bit more of a approachable, let's say, unit. You have ampere per square meter, which is much easier to understand than something like the square root of meter times second times whatever the Butler-Former rate has in its units. So this is, I think, an improvement just for understanding the calculations that are going on. In this case, you can see how we fitted our maximum exchange current density against data which we got from Anja Bielefeld from University in Giessen. So we take this data, we analyze it, and then we put it into the material database. Of course, it has to be said that you need to put in this information with every pair of active material and solid electrolyte. Okay, these are some of the equations which get simplified, which I just mentioned beforehand. So this is the ASSB cathode generator, which has been presented by Orkun Furat from the University in Ulm before. This will be available in GeoDict 2025. So it will be shipped with GeoDict and you can use it and take a crack at it yourself. With the new model structure. So on the left, you see the digitized structure. This is the model structure by Orkun and his colleagues at Ulm. We can see, I think the resemblance is quite big with these two. So it's a good representation that he found. And the virtual model is going to be a parametric one. So in our final aim of this is that we allow you to really take a identify the different grain sizes and that you have a parametric model where you can say, oh, let's say my grain size distribution is a little bit on the larger side. What effect does this have on my battery simulations? So this is an important step that we not only got one model that works with a couple of AI-infused parameters, but these are actual parameters that you can put into your research. All of this has been collected in a publication that we did together with Ulm University, and it is submitted and will be available soon. With that, I want to thank our collaborating partners in Gießen, Ulm, and RJL Micron Analytic. I want to thank the Federal Ministry of Education Research for funding this project. And I would like to answer any questions if you have some. Thank you very much.